Hello, my name is Untitled Paz. I'm here with my team members.
Alejandro Parros.
Daniel Duncan.
And we're Dynamic Engineering Solutions. For our senior design project, we did the ShellEcoMarathon. You're probably wondering what the ShellEcoMarathon is. It was by two scientists from 1939 where they wanted to see whose car could go the furthest on 1 gallon of gas, well, in liter, because it was in Europe. And from there on out, it was a competition that they hosted in other colleges, and FIU is now participating in it now. Right now, the competition vehicle that holds the most MPGs is called the Pack Car, which holds over 15,000 miles per gallon. Now, the competition itself, since we also know that there's many other fuel alternatives, we have hybrid cars, we have liquid propane gas, gasoline, electric. So for our project, we did gasoline fuel, and so the constrictions for this project is you have to maintain a speed of 15 miles per hour around the circuit for as long as you can on the amount of gas that they feed you. And right now the competition is in Texas, and it'll be hosted in April.
As far as our global learning aspect goes, that's one of the most important factors, especially for this project. You know, from the beginning, we know it has to be an economic vehicle, not only for transportation. You know, it's for a single passenger, but also for fuel efficiency. It makes you wonder what type of fuel you're going to use. Of course, that's the reason this competition exists as well. Beginning with the two scientists that were kind of bidding with each other on which car would travel first distance on the amount of fuel that they were using. Some cars have achieved distances from Paris to Moscow, and of course that's about 1,500 miles on a single liter of fuel. That's one of the other requirements that we need for the fuel amount. For the event itself, it happens annually in the Americas, Asia, and Europe. For our car specifically, it's going to participate in the April 24th through April 27th American division of the competition, which, as we mentioned, is in the streets of downtown Houston, Texas. Our team goals. Initially, what we wanted to change, this is a car that is from the team of last year of the ShellEcoMarathon. It was involved in an accident to begin with, so of course we had to consider the structure of the vehicle. From there, we wanted to prioritize the aerodynamics and the lightweight aspects of it, and from there, if we had time or we needed to make any changes, we were of course going to work on the fuel and the power itself of the vehicle. Our team objective, of course, was to apply our engineering knowledge, promote our teamwork skills. This is our first fabrication project for most of us, the senior project in general, so of course we were going to learn from it, how we were going to apply different aspects to the vehicle based on the design we made. We wanted to produce a competitive vehicle, especially one that would complete the competition, because for the past few years, none of the vehicles have actually completed an entire lap around the circuit. So that's one of our biggest goals, and of course become better engineers through the experience that we have developed working on this project.
You can see the need for eco-friendly vehicles around the world. The car sales and productions are increasing in major markets like China and India. You can see there's some pretty drastic increases, while there's a slight increase, not as big increase in the Americas, the United States and Canada. This is relevant for the global learning because fuel efficiency can be applied all around the world, not just in the U.S. So whatever fuel efficient product you can make, you can improve, you can maintain, is something that can be applied to the whole country in general, the whole world in general, not just this country alone. Right here is another demonstration of why we need fuel efficient vehicles. Right here is oil production from 1920 to 2010. We can see that oil production is increasing drastically through this period, and around 2000 is expected to peak between 2000 and 2010. The problem with that is that we're producing more cars and we're running out of fuel, so we need more fuel-efficient vehicles if we're going to maintain the society. And that's a big engineering challenge we're hoping to participate in. So the tasks and timelines, you can see the different operations, how it's distributed between the group, from research to requirements. Engine selection was on Alan. Chassis design was mine. I did a lot of work on the steering components, the rebuild, the body, the materials. Here's our updated timeline for our project. And for everything we've done for the past year.
Well, for the past vehicle, we mentioned that we're taking from the 2012 EcoMarathon. We're mainly taking their frame. They made it to the competition and they actually took a turn too tight and they crashed. So the frame was all, it kind of was a little bit torsion, tires were breaking off. Here's the photo we have of it in the machine shop, right just as we got it. Here's them actually at the competition. And the whole car itself encountered many problems. Many problems from the way you actually hold the steering, from the throttle. Going back to what I just said, the steering configuration, it rested on your left-hand side, and where the driver pulls it upwards, you make a left turn, pull it downwards, you make a right turn. It was very unconventional, very not standard. And then on the right-hand side, you had a lever, much like an airplane, that it was pointing upwards, where you had to apply a torque clockwise to apply gas to the engine. Very, very strange maneuver if you're inside the vehicle, and so very unethical. However, in the remodeling, we have a chariot type vehicle. The first vehicle, it had, like the Romans had, it had a horse and a buggy, and the steering was like a chariot. That was one of the first ones, and they didn't do that well neither in the competition. Here they had a push-pull system. Here's actually a photo of the throttle that they configured at a 90-degree angle that had that upward shape. And for our renovations, we have, this is the car semi-done. We have other components on the steering. We have a new bicycle handlebar style, very simple to use. We use the KISS principle, keep it simple. And we have the braking on top of the throttle for the back brakes, and right now we have the front brakes attached to the left-hand side of the handlebar. So in this photo, we can see that the angles of these tires are not using the apex of the tires. If you're not using the apex of the tires, you're not using the full structure of the tire. So what we had to do is we had to fix the curvature, fix the hubs that they used to get a perfect 90-degree with the floor.
These are the wheel hub components from the previous design. In the upper right-hand side, you'll see the spindle where the wheel rested, and you can see the pivot for the spindle is actually the 12-degree offset from a straight perpendicular. And that right there on the bottom is the hub that mounted into the pivot on the frame side. And when you installed the spindle into the hub, it rested up at 12 degrees. And that's why you saw in those previous pictures the wheels had an excessive camber in. We wanted to compensate for that, so we redesigned and we had fabricated new spindles. You can see here, this is our shop drawings for the production. We had a rod milled down laid down to 7/8 diameter to fit inside the tube. And we had a sheet metal bracket cut out and brake formed to meet that shape of fitting the spindle. And it was offset at 10 degrees. The intent was to give us an overall camber of -2 degrees, which helps with handling around the corners. And right there's a picture of it installed on the car, and you can see that it's a lot better. It's not the 12-degree offset they had before. Now you have 2 degrees. You have just the right amount of camber. Next slide. Out of the body, you can see this is right after we got it, we removed some portions of the frame that were damaged, they were in the way, they were to do the redesign. We modeled it in SolidWorks as it lies there, so we could build a body around it. So we could design our body, design our steering system, and get a real 3D model and a real feel for the car before we produced anything to make sure everything works.
Here's some prototypes that we had. We had a soapbox design for easy exit and entering. It really didn't last that long. We don't want to close the engine because it's forcing duct air, and if we close it, it will just overheat. So this prototype was thrown out. Our next body design coming up was more of it was still enclosed, and it was very hard to manufacture to get mold of it. And so they told us the best way to do it is to chop off the end, and it's all free, how I meant it for it to actually breathe. So our final body design is as shown here for still easy entering and exiting, and so that it will slide right into the frame from the previous team.
I want to continue with the body design. First of all, one of the biggest challenges for us was, as you saw in the pictures from the team of this past year, they had a female driver that was also very short in height. So it was very difficult for us to immediately, myself, Alan, to fit in the car. So that was one of the components we immediately decided to get rid of the body frame of the car, is we had to take out the structure bars going from the back body, basically at this point up to the front, because we just couldn't fit in the car. What this is here is a foam mold. We want to thank Howard Direct for providing that. We designed that mold for them using SolidWorks to set the dimensions. They molded the entire body for us because our body is made of carbon fiber. That's the process that we took here at the machine shop. Standard epoxy process. We were applying the carbon fiber on top of the foam mold, and that's how we got our body construction. This is the beginning of our building process. We're still designing the steering there. We are recycling many components that we removed. That's that long bar of the steering on the left-hand side is actually part of one of the bars that we removed. Of course, we're applying the new reinforcement. We have the wheels in place, and that's the bottom shell of the body, which is of course made of carbon fiber. This is a final picture of our assembly. Of course, as we mentioned, the engine compartment is open in the rear. We have the back support, a lot more space for bigger size drivers. It's a lot more convenient to get into the vehicle and out of it. And once again, everything's made out of carbon fiber. We kept that lightweight component. And the silver rods are also aluminum, by the way. So, they were using carbon fiber before. It didn't have as much strength. We've used the aluminum rods, the joints and everything. We made sure they weren't loose, they weren't moving, and everything works well. It supports our weight.
We did some preliminary CAD simulations using CFD and SolidWorks. This is actually the first prototype that we tested the flow across, and we tested it at 15 miles an hour, which is the track speed at the event in Houston. So this is modeling real-world conditions of what our car is going to be driving at. And from it, you can see, points obviously like the back of the seat where you're going to have flow problems, where the flow gets caught inside the body. And you can see in the rear of the car the reduced flow rate. Basically, from that we try to modify the final design. We try to take a little advantages from that to modify the design to make it a little more aerodynamic.
Last week here we have our expenses that it cost us. We spent over $1,500 for our project, and we believe right now that we are race ready to go to competition. Just a few little steps like to replace the horn, put in seat belts, little miscellaneous items like that. Any questions?
Very good. On that last slide where you show the cost, you say you're race ready. Well, how do you get the car to competition? Where's the transportation component of the cost to get it to Houston?
I have very different ways to actually get there. I'm not actually going to take it to competition since I'll probably not be here at that time. But I know through the A&S system at FIU, they could probably sponsor your whole project over there. If anything, they'll do what last year's team did, where they took out their own money, paid a rigging company to take it over there, and all their expenses were paid by themselves. But I was trying to get FIU to sponsor our project first.
Okay. Any other questions? Dr. Abel? Not here? Dr. Tremont.
Question. The motor on that system, how fast can that car go?
From last year's, they told us not to touch their engine because they were very antsy about it, that anything will go wrong. Things still went wrong. In the machine shop, we had items stolen from it actually. So it was very strange. So I didn't touch anything there, but from what I know, it's a 50cc 4-stroke engine from this book. So I imagine maybe max speed 80 miles per hour.
And thus comes my question. If the max track speed is 15 miles an hour, why are you putting an engine that can go 80 miles an hour? Because it's got to weigh something. And I would assume that if you had an engine that was capable of running around 20 mile an hour or less, you would get yourself some weight gain, which would obviously convert into distance.
I understand where you're coming from. I would love to put a lighter, engine with lower horsepower and make much more fuel efficiency, but they told me not to mess with their engine. If I could, I would have bought a more fuel efficient engine that's lightweight, probably from like a lawnmower, and from there,
I think
go around it.
the idea behind it was when they originally put that motor in was availability. You could go online, you could order a motor for $300, come with a transmission, torque converter. It'd come out of the box ready to install in the car. I think that's what originally was the design idea. And we inherited it from last year, and we try to do our design modifications on the steering, on the body, on the frame. We try to focus on those elements because we were advised by the previous team to leave the engine as it was because they were attached to it, I guess. And we focused on other things.
Dr. Levy?
Yeah. The final design has it open like that in the back.
Yes.
Yes.
What about the, maybe the drag would be kind of low based on the fact that you're going that slow, but wouldn't you be saving something if it was somehow closed, or if it was closed?
We did want it closed initially. However, from Hotwire Direct, they told us if we enclose it, it will take the process to take off the carbon fiber from it will take forever, and then it will be stuck there. And then we can't have foam with carbon fiber and buy at the same time because the foam's into place. So we had to deal with just cutting it off completely from our project.
Which was already difficult. We struggled a lot. I mean, this for all three of us at least, this was the first time we were dealing with carbon fiber, and at one point we were actually painting it outside of the machine shop there, and the sun actually cooked the carbon fiber onto the foam. So we struggled even more to remove the carbon fiber from that foam mold, but we got it off thankfully, and everything was in place, and we put it on. This is the final design.
Did you guys do any kind of simulation with and without let's say, a back cover of some kind?
We did simulation with the original design with the cover on the back, and we were prepared to go with that. Like Alan was saying, that when it came to actual fabrication and producing that carbon fiber shape and the styrofoam, that's when we decided to remove it, and we never got back to doing a second CFD on the current final design.
So no, just to piggyback on Dr. Levy's question, so you've got no CFD results demonstrate the aerodynamic efficiency of this particular body. You have not done that.
We have, only thing we have is from the previous design, which is, the final design is based off of it. So we have an idea, but we don't have actual analysis.
How difficult would that be for you to run a CFD?
Oh, we'd have it ready right away. We have all the designs. We have everything organized. The whole process. We have every single change that we made. We have it saved.
So you really don't know the CD for this then, right? No. Okay. All right, any other questions? Hearing none, thank you. All right.